Hi, I am Simone Bordoni, and I will tell you about my recent work on the application of reinforcement learning for the noise characterization and simulation on quantum devices. In this work, we want to teach a reinforcement learning agent to reproduce a particular noise model, and we want to do it with minimal heuristic assumptions. In this way, we can get a superior performance with respect to standard techniques, for example, randomized benchmarking, and also we have enhanced generalization properties. Going more in deep with the algorithm implementation, what we do is that at every epoch, we give a quantum circuit to the reinforcement learning agent. This quantum circuit is without any noise channels. Then, for every circuit moment, we let the agent perform an action that consists in placing an error channel with the chosen parameter. At the end of the circuit, we compute the density matrix of the noisy reconstructed circuit. We can access the density matrix if we are doing a simulation, or we can extract the density matrix, for example, using quantum state tomography or similar techniques. Then we have to compute a reward that will be a measurement of the distance between the reconstructed density matrix and the original density matrix. We found it empirically that the best reward function is based on the trace distance, and in particular is given by 1 over the trace distance squared. There is an important detail that is the quantum circuit representation, which means encoding the quantum circuit into a vector containing all the features of the circuit. For example, in this case, we convert the circuit into a three-dimensional vector, where the first dimension denotes the qubit, the second dimension the circuit moment, while the third dimension encodes all the characteristics of the gates that we are using. In this particular work, we are using Rx and Rz single qubit gates, CZ for the two qubit gates, and then we are letting the agent the possibility to add depolarizing amplitude damping channel and also coherent Z and coherent X errors. Here we can see some results of the training for in the single qubit case and 3 qubit cases. And in top, we can see the training obtained on a simulation. So with a noise model, a simulated noise model, where we consider a gate-specific noise. And then in the bottom, we can see the results obtained on 1 qubit circuits on a real quantum hardware, in particular the Quantware chip hosted at the Technology Innovation Institute. After training, we have benchmarked the algorithm, and we have tested it on circuits from depth 3 to depth 30 on simulation. And we have compared the results with what we get with randomized benchmarking. So projecting all the noise as the polarizing noise. We also repeated this benchmarking for qubits spanning from length 5 to 50 on the quantum hardware. And also in this case, we can see that there is an advantage with respect to randomized benchmarking, as the matrix fidelity is better with respect than the matrix fidelity obtained with the randomized benchmarking. And we have, as an additional benchmark, we have also tested our algorithm on renewed quantum circuits, like the quantum Fourier transform or Grover's search algorithm. And we have performed several tests. Here it's reported the shots obtained with this algorithm, this on simulation. And we can see that our algorithm is able to better reconstruct the peaks, while the randomized benchmarking tends to flatten the noise. In conclusion, we can say that we have demonstrated that our reinforcement learning-based approach has better performance respect of classical heuristic techniques, and it also adapts better to different noise models. There are a few problems with respect to this algorithm that will be addressed with future developments. In particular, the key challenge is the scalability to many qubits. This is due to problems with the exponential growth in the action space and also in the measurements requirements in order to get, for example, the density matrices on real hardware. We are exploring different approaches to solve these problems. For example, using, partitioning the circuits into small subcircuits, each one addressed by a different agent. Or also the possibility of employing graph neural networks for encoding larger circuits. Here you can find a published paper, and there's also a GitHub repository where you can find all the code used for the simulations. Thank you for your attention.